The next thing we're going to talk about is the remainder theorem. But before I just tell you what the remainder theorem says, we're going to do a little bit of exploration by evaluating and dividing and seeing what we can find in common between these two processes. If I was asking you to evaluate this function at x equals -4, then I'm just going to plug in -4 every time I see an x. 2 times -4 cubed plus 7 times -4 minus -4 plus 12. This gets me 2 times -64 plus, that should be squared there, 7 times 16 plus 4 plus 12. And I'm getting -128 plus 112 plus 4 plus 12. And f of -4 turns out to be 0. Which doesn't seem that bad, although some of these numbers in here got a little large, especially if I didn't have a calculator on hand. Next, I want you to synthetically divide 2x cubed plus 7x squared minus x plus 12 divided by x plus 4. So inside my division bar, I'm going to put the opposite of +4, or -4, and then all of the coefficients of the numerator, or dividend. Drop my 2, multiply to get -8, add down, you get -1. Multiply to get +4, add down, you get 3. Multiply to get -12, add down, you get 0. So my answer would be 2x squared plus -1x plus 3 plus no remainder. Okay, what do you see in common about these two processes? And this is where I would usually have my students call out, but I understand we're in a video setting here, so you can't necessarily call them out. But one thing that my students usually see is that we started off with the same polynomial as the same numerator. So f of x in the evaluate step was equal to my numerator in my synthetic division problem. The next thing you also see is that you're evaluating at x equals -4, and you're dividing by x plus 4. But the -4 appears in the synthetic division process as our c. So the number that we are evaluating at is the same thing that we're dividing in our synthetic division problem by the factor x minus c, but the -4 is the c. So the evaluate at c, and it's the same thing for the c that you're dividing by. And there's one other similarity. Notice that my answer to f of -4 was equal to 0, but also that my remainder was 0 here. So that's the last thing that I wanted you to notice that was the same. So f of c turned out to be the remainder in my synthetic division problem. Let's see if these things happen again using a different problem. Next, I'm taking a different function and I'm evaluating it at -1. And I get 2 times -1 plus 7 times +1 plus 1 plus 12. -2 plus 7 plus 1 plus 12 is equal to 18. So f of -1 is equal to 18. Using our synthetic division, I'm taking the same polynomial as in my numerator, or my coefficients, my synthetic division process. I'm dividing by x plus 1. Inside my division side, I'm going to put a -1. And I'm going to divide by dropping the first coefficient down. 2 times -1 is -2, add down to get 5. 5 times -1 is -5, add down to get -6. -6 times -1 is +6, add down to get 18. My answer here would be 2x squared plus 5x minus 6 plus 18 over the original divisor. What do we see in common again? Well, we've already decided that f of x is equal to the numerator on the first problem. Is that true for the second problem? Does the f of x equal the numerator? Sure it does. Secondly, I'm evaluating at c, or -1, and I'm also dividing by x minus c. That c and that c are the same. And lastly, we can identify that the f of -1 is equal to 18, and when I divided by x plus 1, my remainder was also 18. So I can say that f of c is equal to my remainder. So if I'm trying to evaluate a large polynomial at a point x equals c, instead of doing all the evaluation, I could synthetically divide to find the remainder. A question I usually like to ask is, which process is easier? Is it easier to plug this in and find out all the large numbers? Sometimes it might be fine, but sometimes, look at these numbers, got really, really big. I find it often it's much easier just to use the synthetic division and find the remainder that way. Well, we have just explored a little bit about remainder theorem, but let's actually define it. The remainder theorem really is identifying that f of c turns out to be the remainder as long as you're dividing by the same constant c. So the remainder theorem says if you have a polynomial f of x and it's divided by x minus c, and it yields f of x is equal to the quotient times x minus c plus the remainder, which we practiced in the last page, then we can say that the remainder, r, is equal to the value at f of c. Or f of c is just equal to r. That's another way of saying it. So I can show you why this works here, and this is kind of like a mini proof here. If I have the f of x equals x minus c times the quotient plus the remainder, it's the same thing I wrote up here, just the terms are switched around, and I want to evaluate it at c. Well, if I plug in c for every x that I see, instead of x here, I'm going to plug in c minus c times the quotient at c plus r. Well, I don't really know what this quotient at c is, but I do know what c minus c is. And c minus c has always been 0. So f of c is equal to 0 times the quotient at c plus the remainder. Well, 0 times anything, I don't care what this quotient at c is, it's going to be 0 because 0 times anything is always 0. So therefore f of c is equal to my remainder. So let's use the remainder theorem to evaluate at f of c. So I have f of x is equal to this very long polynomial, and I'm trying to evaluate it at f of 5. Now, I could plug in 5 for every single one of these values. I might want to get out a calculator because it's going to be quite large. -5 cubed and 5 squared times 11 is just something I'm not going to want to do in my head. So instead of actually plugging it in, what I'm going to use is synthetic division. And inside my bar, I'm going to put the c, or 5, list the coefficients. Notice I didn't take the opposite of c. This c and this c are the same. I don't have to take the opposite. I'm really taking my f of x and dividing it by x minus 5. So this 5 and the c5 should be the same value. I'm going to drop my first coefficient, multiply, add down, multiply, add 7 plus 30 is 37. 37 times 5 is 185, and 185 minus 19 is 166. So I know that f of 5 is equal to the remainder, which is 166. And I figured that out without having to do lots of large numbers. These numbers here at the end got a little large, but I'm promising you that they're going to be less than the numbers you might see in the process of evaluating f of 5. Okay, I'm giving you a different polynomial this time, and I'm still asking you to find f of 5. So inside my bar, I have a 5, and I have all the coefficients of my polynomial. The first coefficient is 1, then a 4, and then a -7. Although we did miss one of the terms. My first term was an x cubed, my second term was an x squared, and my last term so far is an x. Which term am I missing? And a lot of students may say, well, you're not missing anything. We went down by 1 every single time. But you do have to know that if you don't have a constant term, you have to put a 0 there. Otherwise, you won't be able to find out what your remainder is. So now that I have all of the terms from x cubed all the way down to constant, I can finish the problem. Bring down the 1, multiply by 5, add down, multiply 9 times 5 is 45, add down to get 38. Multiply 38 times 5, I'm getting 190. Add down, you get 190. This remainder is the same as evaluating f of 5 and getting 190. I find this a whole lot easier to do the synthetic division than it is to actually plug it all in unless I had a calculator, and then they're about the same. So the remainder theorem helps you evaluate a function at a number without actually plugging in the values, just using synthetic division of that c. Next, I want to remind you about the zeros of a polynomial. We've already talked a little bit about this semester, but I want to remind you that a complex number, c, is said to be a zero of a function if f of that c is equal to 0. And we say complex, it could be real or it could be complex, but zeros could be both, so that's why we use complex, which includes both. If we substitute the c in for x in the function and obtain 0, then we can say that we are a 0 or a root or a solution of the function. Zeros, roots, and solutions are 3 different ways of basically saying the same thing. If I plug this value into the function, I get out 0. So next we're going to use that definition of 0 to determine if this number c that I'm giving you is actually a 0 of the polynomial. Well, in order for c to be a 0 of the polynomial, we just said by the definition f of c must be equal to 0, and then we know we are a 0 of the polynomial. Well, again, using remainder theorem, instead of plugging in -2 into the values, what I'm going to do is I'm going to use synthetic division. And if I get a remainder of 0, then the remainder theorem tells me that f of c is equal to 0, and then I know that I am a 0. So when I'm asked to determine if the number is a 0, well, what I'm going to do is I'm going to plug in -2 as the c of my synthetic division, and I am just hoping at the end of the day I'm getting a big fat 0 here. That's what I'm hoping for. Well, let's go ahead and try it. Drop down the 3, multiply and get a -6. Add down, you get a -4. Multiply, you get 8. Add down, you get 7. Multiply 7 times -2, get -14. And I did not get a 0. So therefore, f of -2 is equal to -8, which is not 0. Which I know is kind of redundant, but noticing that it's not 0, I can tell you for a fact that -2 is not a 0 of f of x. And that is the answer that I was asked to find out. Is c a 0? Well, no, in this case, -2 is not a 0 of the polynomial. Taking a different polynomial, I'm going to do the same process. I am going to put my c, which in this case is still -2, and my coefficients, not missing any. after I work this all out, I would like my remainder to be a 0. I'm really hoping, okay? If it's not a 0, then it's not a 0 of the polynomial. If the remainder here is 0, then this c is a 0 of the polynomial using the definition of 0 and also the remainder theorem. I drop this down, I get 1. 1 multiplied by negative 2 is negative 2. Add down. Multiply, I'm getting 0. Add down. Negative 4 plus 0 is negative 4. Negative 4 times negative 2 is positive 8. And negative 8 plus positive 8 is 0. Yay! That's exactly what I wanted. So I can say, using the remainder theorem, that f of negative 2 is 0. And if f of negative 2 is 0, then by the definition of a 0, negative 2 is a 0 of the polynomial f of x. Woohoo! So now I have determined if this is a 0 or not.